Uh, this is Group 19. My name is Tumel Azepias. We are presenting the project Explainable Artificial Intelligence Deep Transfer Learning for Skin Disease Diagnosis. The keywords are Deep Transfer Learning, Artificial Intelligence, Explainable Artificial Intelligence, Skin Disease Diagnosis, and Convolutional Neural Networks. So, diagnosis refers to any form of treatment a given individual could receive from a medical personnel or an AI-based system. In this case, the skin plays an essential role in an individual's physique in terms of providing protection, regulating body fluids, and temperature. Therefore, this project aims at improving skin disease diagnosis using deep transfer learning and explainable artificial intelligence. So the problem statement is skin diseases cause a huge burden in the global context of health and obtrude out as the majority in terms of global diseases. Existing skin disease diagnosis methods are costly in terms of time and money and require skill and experience and are also prone to errors, which causes misdiagnosis. All this is relative to skill and equipment. So the problem tree here shows the problems that the patients face as a result of skin diagnosis in white, and in red at the bottom, the problems that dermatologists face as a result of misdiagnosis. The research scope. So this study focuses on 5 skin disease class, that is melanoma, eczema, acne, rosacea, and keratosis. We used a deep transfer learning, convolutional neural networks, explainable AI, along with graduate weight class activation mapping, that is GradCamp technique. So I'll end there for now. I have my colleague coming for the literature review.
All right. Yes. So my name is Mahendra James, and during our research, we discovered that 1.9 billion people suffer to conditions that are related to skin conditions that are related to misdiagnosis, and also realized that during a research carried out by the NIH, they realized that skin cancer like the cost for skin cancer is over $1 billion. That's just in terms of treatment. And then also, in addition to that, we have the World Health Research conducted in 2001 that on diseases that are burdensome, and skin-related diseases were amongst the top 5 that were on the list or on the charts. So our research consequentially aims at using explainability of machine learning algorithms to realize solutions to the subsequent questions of how can deep transfer learning be used to improve on predictivity, rather the predictive accuracy in diagnosis of skin disorders, and then also how can XAI, which is explainable artificial intelligence, be applied to the field of dermatology to increase adoption, and also how can deep transfer learning be used to automate skin disease diagnosis using imagery data, and the degree or to what degree at which explainable artificial intelligence can justify deployment of skin disease diagnosis models for public use and also dermatologists. So our research objectives were specifically to pre-process and prepare dermatology data sets for model training, to test and evaluate the deep transfer learning model also, and then also deploy interpretability and explainability rather, using XAI techniques. For our research contribution, we incorporated explainability and interpretable machine learning techniques to provide a trusted model. That is, we have data that is crude, and before that, like you're seeing in the chart over there, models were abstract and there was sort of a black box experience. But now with explainable techniques, humans can be able to interpret the results and know the reasons as to why models have made particular predictions. Thank you.
Hello, my name is Hall Enoch Asanda, and I'm taking you guys through the system design and implementation. So under system design and implementation, we look at the structure of data, the data set. So first of all, we obtained this data set from our DAMET, and our data set involved only 5 classes: the acne, eczema, rosacea, melanoma, and keratosis. Now, the following graphs illustrate the different amount of data that we collected basing on the two folders that we created or characterized this data into. The first category of the data or folder in which this data was characterized was training, and the image on the left shows that, and then the image on the right indicates the training data that we collected, and they are illustrated using the bar graph. So the image below, it illustrates the kind of class that we singled out to look at or to present in these slides, and that's melanoma. So the following image illustrates the process through which the images underwent. For example, these images underwent resizing, pixel normalization, image augmentation. And after that process, they were passed through the VGG16, under which we had a concept of feature extraction. And the output of this model was evaluated and passed through an explainable technique, which was called GradCam, to provide a prediction and explanation. The experimental setup, yes, we actually employ the use of Keras library to implement the networks. And these are, we came up with 3 models that we were used to classify the 5 classes. And these models were fine-tuned by use of hyperparameters. And then when we looked at, we also looked at data argumentation, because our data was limited in terms of 5 classes, yet neural networks need more data. We had to employ the use of a data augmentation concept, where we transform the data such that we can get more of the data for better accuracy. And the diagram below shows the transformations that we put on the images. So fine tuning, under fine tuning, we looked at finding parameters that directly affect the model during training. And after fine tuning them, so what we did under fine tuning, we removed the last layer of VGG 16 and replaced it with a new layer classifier, a new classifier, which is a feature structure, and it classified these input images basing on the activation from feature extraction phases. And that's all I have to say about that.
Okay. So this is Joshua, and I'm here to continue with the system design. So basically, the idea here is that we trained a couple of models during our research, and as part of fine tuning, each set of parameters gave us a different model, and each set of parameters kind of represented how complex a certain model was and the ability. So if you can look at the 3 models we had, the first model had around 27 million trainable parameters. And these basically, our explainability methods were able to explain the results for these models, right? And the parameters that were corresponding for each model. So we used some other metrics in the design, such as recall and precision, to represent how well the model is visualizing on the data. Basically, precision and recall, ideally what we want is that for our models, we would like to avoid all cases where the patient has a disease, but then the model misdiagnoses him. And that means that our focus was more on getting a higher recall, right? And if you can look, our model 3, it had a recall of about 65%. And that's why we actually chose model 3 as the best model in our case. And moving on to explainability, so much as just like our objectives were stating, that a crucial aspect of our research was to incorporate explainability into machine learning workflows in order to not only predict, but also explain the predictions. And in the process, we increase model interpretability and transparency, just like our contribution stated, but also increase the transparency and accountability in the medical field where things could be critical in terms of explanations. So just to give a brief overview, explainability refers to the ability of a machine learning model to provide a clear and understandable explanation. From the background of explainable AI, there are many different kinds of explanations that a model could produce. They could be counterfactual, they could be textual, text-based, they could be descriptive, but they all depend on what kind of problem that you're trying to solve. And in our case, since it's a diagnosis problem and we're trying to classify and predict, it made sense to have visual explanations. Explanations that look at the image and explain it in a way that a doctor would actually explain it. So let's say a doctor looked at an image and then said, okay, this is typically melanoma. Excuse me. So can the model be able to replace the doctor and do the same thing? And then if you wanted to show that the model can do that, what's the best way to represent that? So it would be a visual description. Something like, okay, if the model is saying this is melanoma, then where did it look? And we've also described this in our report and proposal, like as part of our promises. So an example of the outputs from our research could be a classic input like this. So a classic input could be images. So we gave images to the model, and you see that the model was able to use saliency maps to explain the prediction. So it explained the prediction by saying it highlighted what pixels were important for that specific prediction, right? And this is a classical example where it was able to actually depict very well. So this was using CDNC maps. We used a couple of techniques. An example was also another one where you have smooth grad. And with smooth grad, you can see that we were able to generate a heat map of what regions. If you can look at the images in this slide, you see that they correspond. I mean, if you were even a human, a typical human, and you look at these images, you could see that, okay, I would base on these regions to give a given diagnosis. And that's what we're trying to incorporate in this model, accountability and transparency. Where did you look as like in terms of the model, right? So you can see that the model is actually looking in the right places. Also, if you can look at this, this is also a classical example where the model was actually able to to trace out the circle. So here, the image was eczema, and the model actually predicted eczema, but it traced out the spots in the image that that what's the right word? The spots in the image that contributed most to that contribution. So as part of our conclusion and future work, we hope to continue developing much more complex models because as you can see, these models, they had around accuracy of 65% and 67. So we hope to see if we can gain more data, train more models, and achieve much more accuracy. And also as part of our future work, we hope to implement more techniques. Here we used visual techniques like breadcrumbs, CDNC maps, but we can also use LRP. You know, we hope to use more techniques that are global, right? That can give a global representation of the model's accuracy and performance, and as well as explaining all that. So I think that's enough, and thank you for listening to us.